Hello everyone, my name is Changjiang. Today I'm going to talk about this paper on the difficulty of defending against contrastive learning against backdoor attacks. As you know, supervised learning has been widely used in machine learning area. For example, you can train a supervised traffic sign recognition model and apply it in the self-driving system. This is a high-level pipeline of supervised learning. You collect a large number of labeled data, and you use a supervised learning algorithm. You can get a final model. And as an inference time, you feed the test data to the model, and the model can make the prediction. You can get the prediction result. An obvious drawback of supervised learning is that it usually requires a lot of label information, but the annotation cost is very high. It's extremely time-consuming, and sometimes it requires expert knowledge. For example, for the medical images. So the research proposed contrastive learning to address this issue. Contrastive learning is a kind of self-supervised learning. So contrastive learning aims to learn representation by enforcing similar elements to be core and dissimilar elements to be different. For example, for a stop sign image, we conduct the data computation. We can get two views of the stop sign. Because they are from the same source image, we will make them closer in the feature space. But for other image, like the speed limit image, because it's from the different source image, we want to make it far away from the embeddings of the stop sign. So this is a high-level idea of contrastive learning, and we often use contrastive learning to get a pre-trained model. And after we get the pre-trained model, we can fine-tune the classification head on a small number of the labeled reference data. This can greatly reduce the annotation cost, and we can get the final model. This final model, we can use it like what we used in the supervised learning. A popular risk of supervised learning is backdoor attacks. At the inference time, we just need to attach the trigger to the labeled data, and we perturb their label to the wrong target class, and we can get a poisoned model. And at the inference time, any images with the trigger will be misclassified into the wrong target class. But in contrastive learning, since we cannot access to the label information, so the researchers often only poison the target class. So they collect a small number of reference target class examples and attach the trigger in these examples. This is kind of like the human-created bias. And after the pre-training, we can get a poisoned pre-trained model, and we use a small number of labeled reference data to fine-tune the classification model. We can get the poisoned final model. And based on the trigger definitions, we can divide the backdoor attacks into three categories. The first category is a universal trigger. And the second kind of trigger is a functional trigger. For example, we apply the frequency signal as a trigger. And the last one is a dynamic trigger. For different inputs, it has different triggers. So this is three kinds of trigger definitions. To address the threat of the backdoor attacks, researchers propose different kinds of backdoor defense. Some of them focus on the learning dynamics. This means because the poison examples and clean examples behave different learning curves during the training. And some others focus on the feature distribution because the clean examples and the poison examples have different feature distribution in the embedding space, so it can be used to detect the poison examples. And some other focus on the downstream tasks like the reverse engineering, the neural cleans, the strip, and the fine-tuning. So we have a question is that how do contrastive learning fundamentally differ from their supervised counterparts? The second question, what are the implications of these distinctions? And the third question is, it is possible to defend against contrastive backdoor attacks. So to compare their difference, we first propose a general attack framework. It contains two processes. The first process is select candidates. There are typically two ways of selecting candidates. The first is to select candidates from all class, and the other one is select only from the target class. And according to the trigger definition, we define a process of applied trigger. So there are, according to the trigger definitions, we have three kinds of trigger. And this figure shows a threat model after the attacker pollutes a small number of poison data, and we use supervised learning and contrastive learning trained on this model. We can get a backdoor model, and any trigger input will be misclassified. First distinction we found is learning dynamics. The first three columns show the learning dynamics of supervised learning. We can see that the red line, this is the north curve of the poison data. So we can see that the poison data, the north of poison data drops very quickly. This is because the backdoor task is much easier than the normal task. So they drop very quickly. So we can use such feature to detect the poison examples. But for contrastive learning, this is not that case. Their learning curves are entangled. So they drop at the same pace. So this is the first distinction. And another distinction is that in contrast backdoor attacks, the poisoning and clean data are highly entangled in the feature space. For example, in the supervised learning, the black cluster is the poison examples. It is not necessary to be close to the red cluster. This is the target class because we have label information. We just assign a label to the black cluster, so it can attack successful. But in contrastive learning, because during the fine tuning, we only assign the label to the red cluster. So the black cluster should be close to the red cluster. Only in this way we can attack successful. So this is their difference. So in contrastive backdoor attacks, the poisoning and clean data are highly entangled in the feature space. And we evaluate different kinds of defense. The first is anti-backdoor learning. So in anti-backdoor learning, it uses the feature that poison examples, the loss of poison examples drops very quickly compared to the clean examples. So for example, we can see here, in supervised learning, it can achieve very high true positive rate and no false positive rate. But it is not effective in contrastive learning. This is because their learning curves are entangled. And we also evaluate the feature distribution based defense. For example, here is a fine-tuning method. In supervised learning, we can find a threshold that can achieve no attack success rate and high accuracy. But in contrastive learning, we cannot find such a threshold that can achieve the no attack success rate but high accuracy. This is because the poison examples and the clean example activate the similar neurons. And we will also evaluate some other downstream defense like the strip and backdoor defense via decoupling. All of them are ineffective. This is our evaluation, but we evaluate extensive defense, but due to the limited time, we just present some of them here. To defend against the backdoor attacks in contrastive learning, we propose a potential promising defense. This is a density-based defense. So we first measure the intra-class distance and the inter-class distance, and we normalize it. We find that for the poison class, its distance is much smaller than other class. This is because the poison examples forms a much denser area in the feature space. So we can use the density-based clustering method to filter out those poison examples. We use the DB scan to filter out the most denser area, and we can achieve a high true positive rate here, about 99%. And after we filter out those examples, we train the model on the remaining data set. You can see from this table, we achieve a very low attack success rate and high accuracy. So this is our proposed defense. And then the summary, the conclusion section, we reverse key distinctions between supervised and contrastive backdoor attacks using a unified framework. And we evaluate existing defense and identify the challenges in defending against the contrastive backdoor attacks. And we propose a promising defense strategy and identify potential directions for defending against contrastive backdoor attacks. Thank you for your patience. Any question?